Hello, hello. Good morning, good morning. Let's see. There she. All right, there is Annie. Good morning, good morning. And there is and good morning, Savannah. And thank you,
Good
Savannah. I
morning.
know you were here for a million years. I totally appreciate that.
Good morning, Professor.
And good morning, Josh. For the All right, so we have Annie for the double, Savannah for the double, Josh for the double. Thank you all. Wait, then there's more to come. Um. Oh, Andy for the triple, I think. Okay, sorry. And yes, again, thank you. I'm not trying to, but I am. Good morning, Aiden. My bad. Where's Aiden? Yes, good morning, Aiden. Okay. Awesome, awesome. And Maya. Good morning, Maya. Oh, okay. All right. So for good or for bad? And there's Ryan for the double, for the triple. Good morning, good morning. All right. I want to get going. I I felt a little sting in my heart and in the room that I haven't gotten over when I once again postponed that assignment for the very last time. I postponed that assignment. And I think it justifiably irritated at least one person, as I say, justifiably. I felt the irritation and I felt that that was justified. So I apologize. So we're not going to postpone it any more. What that means is today, I want to get straight. I want to finally just say whatever it is that I've been wanting to say or trying to say about the complicated idea of the arrow of time. Um, so I, so forgive me, this is going to be a little bit lecturish or something. Oh, wait, I'm not even sure. Okay, I should. I'm not even sure. Okay, not sure what that means. I'm reading right. I don't even know if that's good or bad, but okay. But yeah, so what I'm going to do, okay. So what I did, right? Okay, the arrow of time assignment, which many of you have turned in now. Oh, and if you just turned in, and I normally you would get a bunch of points right away, right now for that. I did not even do that yet. But I see that a bunch of you turned it in. It is due the very next class, Tuesday. I don't mean to suggest by continuing to postpone it, I don't mean to suggest that it's some huge assignment. I don't, you know, half a page to a page is all I'm looking for here. And um all that. But yes, at this point, I'm asking when you write it up, if you haven't already, to try to relate your answer to the question, to the prompt, try to relate that at some level to the two box problem. That's one thing I am asking at this point. But again, the reason I just keep postponing it is because I feel like there's sort of a punchline or an explanation that I wanted to provide for you to think about before to have fully in your grasp before writing that up. So and I sort of keep getting close to that punchline, but not quite getting there. So that's what I'm going to do now. Double tap the screen. Oh, double tap. Okay, I think I did it. Okay, sorry. Um, so yes, forgive me. I'm going to just try to explain this thing. Oh, thank you, Savannah. Okay. What I'm saying is, in your write-up of the arrow of time, please try to relate your answer to the last assignment, to the Newcomb's problem, the question of the box A, the box B. Like that assignment you already did, which is not to say you couldn't still revise it or still turn it in a better draft. But there was an assignment about two boxes and a choice you have to make with regard to the two boxes. Um, and it seemed to have nothing to do with anything really but then we discussed it for a couple of days, and somehow our discussion of the two boxes led to this next assignment. Somehow our discussion of those two boxes led to this current discussion of heat, temperature, and entropy. um Now that's like a hard connection, and I'm going to repeat that connect, or I'm going to try to spend the next few minutes elaborating on that connection. But what I'm saying, Savannah, and anybody else who's asking, is once you write up the arrow of time, you'll really show me that you really are following the class or the class material. If in your answer to the prompt about a box of dice, if somehow you can show how that is related to a question of $1 million or $1,000, then you'll really show that you're following the trajectory of the class. So that's what the answer to Savannah's question is, in your answer to the arrow of time prompt, please try to make some mention or reference back to the two box problem and show how they're related. If you've already turned in the arrow of time and you already did that, ignore me. But if you already turned it in and you didn't do that, you can wait for me or not to submit a revision, including that. Just remember, please, what I want to reinforce to everybody is every time you do a revision in this class on anything, on a minor assignment or particularly on the big poster research assignment, you always want to leave up your old draft and then add your new revision. It's best practice all around for learning and for your grade in this class. So, okay. So hopefully that answers Savannah's question. One second. Okay. So maybe let me know, Savannah, if that answered your question. I'm not sure. But okay, what I'm going to try to do now is kind of good. Thank you. All right. And that's points right there. That's closing a conversational path. Thank you. Okay. Here's the summary of what I've been sort of trying. So these equations on the front are the equations I'm trying to ultimately explain to you. It's not that I'm asking you to memorize equations or do math in this class or something, but the equations are the most efficient um, uh, ways of expressing these large ideas that I'm trying to get across. And the equations sort of also show that the ideas are grounded somewhere. They're not just a stream of consciousness on my part. So the two top equations are the ones that were written on the board yesterday. I'm going to try to re-explain now, and then the bottom one is the ultimate punchline here. So okay, so let me explain the symbols. Just to remind, first of all, anytime you see a triangle in science, in physics, in math, the triangle is the capital Greek letter delta. It stands for difference or change, always. So when we see a delta, we mean change in or difference in two values of a variable. When you see a Q, a capital Q, in chemistry or physics, it means heat. When you see a capital T, generally it means temperature. And then when you see a capital S, it means entropy. Now, these three ideas are very, very related, but it's kind of the relationship. It's ultimately entropy that I'm trying to explain here. You've all heard about entropy before, I think, but I'm trying to give a slightly more specific understanding of what entropy is. So the thing I was saying yesterday is that heat and temperature are not yesterday, Tuesday. Heat and temperature are certainly very related, but ultimately they're not the same thing. Ultimately, heat is something that flows from one system to another. Temperature is a description at any given moment of a system. I'm going to say that again. And again, I'm going to say that again. Heat is something that flows from one system to another. Heat is something you can add to or subtract from a system. Temperature is a description of a system at a given point in time. Technically, temperature is known as a state function. It describes the state of a system at a given moment in time. That's what temperature is. Oh, good, Clive. 1 second. Awesome. Give me 1 second. Whereas heat is, generally speaking, we talk about it as something that like, in other words, you add heat to a system in order to raise its temperature. That's generally the way we talk about these two things. And then that leads to another level of distinction I'm going to make in 1 minute. But Clyde, yes, go, sir.
Hi, thank you. So does that mean that heat cannot exist by itself? It always has to be attached to another form of life or like form of like substance.
Oh, that's a great. Yes. I mean, the short answer is yes. First of all, great question. Second of all, yes, Ryan. Ryan's the multiplayer co-op king. Not that it's a competition. That would be a contradiction. But yes, Clyde, Question King. Yes, yeah. It- uh, Something like heat cannot exist in and of itself, and that actually kind of relates to I believe it was Maya's question Tuesday. I believe it was Maya. May also have been Sunera. Like if you don't have stuff you can't have heat. That is correct. And we're going to get, by the way, one of the next assignments coming up is called unthingy things, and it will get us into that. Like some things in the world are more thingy than others, believe it. And there's obviously technical terminology for that. But yes. So yes, short answer, yes. You cannot, if you didn't have stuff like molecules, you could not be talking about heat. Now I'm going to go a step further then and say, okay, and I said this on Tuesday, but if you have a bunch of molecules in a container, let's say in the form of a gas, often that's easier to sort of picture and talk about in these contexts than a solid. Say you have a gas um, in a container. Um, the more all of the molecules, so you look at that gas macroscopically, you're like, oh, here is a gas in a container. What we come to believe in science is that if we looked at it super closely, like with an electron microscope or something like that, or various other strobes, we would see that this macroscopic system, this macroscopic gas, is actually composed of lots and lots of little particles, micro pieces. The more the micro pieces are moving around, jiggling around, the hotter the whole system is macroscopically. The more microscopic motion there is, the hotter the system is macroscopically. I'm going to say that again. In other words, the macroscopic sensation of hotness is a outward manifestation or like outcome of the inner activity, the micro activity of motion, right? I mean, and I think many of you have heard that before in many ways in high school chemistry and this and that, but it's like worth pausing for a second just because it is kind of a deep idea. Like we're kind of saying when one kind of thing happens on a micro level, like moving back and forth, like what you might call velocity or kinetic energy, if you like little things are moving back and forth. But then if you zoom out far enough and experience them on a human level, you don't just experience a bunch of motions, you experience this whole other sensation, which we describe as hotness. Like I don't know. I mean, I'm saying that's true. I'm saying we've come to believe since the turn of the 20th century that that's true. I'm not saying it's obvious. I'm saying that we now believe it's true. And it's sort of interesting that one sensation, motion, sort of morphs into a different sensation, hotness, once we go to a high enough scale. Okay, so you know, and again, you don't have to, and this course, we're not prepared. I can't prove that to you really. So it's not that you have to accept that. You just have to accept that a lot of people accept that. And that's a way we look at the world. Okay, but therefore, then it leads to other subtleties. Sorry, per micromoves, right? Then it leads to other subtleties. It leads to this idea that actually, like hotness is one concept. Hotness. Oh, it feels hot. Ow. Right. But but as I said a second ago, if you've ever boiled water at home to like make pasta or something, like there's a different. You add heat to the water. You add heat to the water with your the stovetop. You add heat to the water. You add energy to the water, and then on the whole, the water seems to go up in temperature. Like literally, you could put a thermometer in the water, and then you see the temperature rise. Like they're not one and the same thing. The heat is the input, the temperature is the outcome, right? They're not exactly the same idea. And what is the difference on the microscopic level between the heat that's flowing in and the temperature that results? Well, they argue what we believe is like what we're doing is but when we add heat, we're like jiggling around all the molecules. We're like pushing them back and forth with other fast moving molecules. And then as a result, on average, all the molecules are now in after we've pushed them more and added more sort of energy to the system, they're now moving more on average, so they're hotter. What I'm trying to say is a subtle difference that's being well, a subtle difference. Hold on. A subtle difference is that heat is something you bring to the whole collective of all of these molecules, all these water molecules that you're boiling, let's say. Temperature is the average amount of motion, the average amount of motion in all the molecules. In other words, to put it real, and I think there's something in the chat, I'm going to look in 1 second, to put it as concretely as I can, the subtle distinction between the heat of the whole thing versus the temperature of the whole thing is that if you did exactly what you just did to a bigger pot, like if you had the same type of water and you did the same process to the same type of water, the bigger pot would have more heat if that many more molecules were moving that much more fast, there'd be more heat. But if the fastness of them all was, if they were all still moving the same rate as before, if the average rate was the same, then the temperature would still be the same. A bigger pot at the same temperature as a smaller pot, they both have the same temperature, but there's more total amount of energy of motion in the bigger pot, i.e., it takes more heat. Put another way, if you're boiling a huge thing of water for pasta, you know from experience, it's like takes more time. It takes more to get that huge pot up to boiling point than a small pot, right? So more heat is required to get to the same temperature because heat really is the total amount of motion of all the pieces, whereas temperature is the average. That's just, I'm just telling you, like, I'm not saying that's fascinating. I'm just like, that's how the language is used in science. And it's an important distinction to bear in mind. We add heat to something so that it goes up in temperature. That's like the first thing I'm just trying to say for what it's worth, but there's something in the chat. Oh, yeah. Well, so heat is the weighted average. That's interesting. I see what you're saying, Annie. Um,
No, can I take it back?
oh,
I think that was a brain fart. I think it's supposed to be like the sum. It's not average at all, right?
Phew, yeah, I think that is better. Yeah, you just saved us both.
Yeah.
Okay. Whew, I love the concept of weighted out, but yes. All right.
I saved myself. Did I redeem myself?
All right. Awesome. Yes. Well done. Good dialogue. All right. But that does show, but the whole thing that Annie just did also does show she's right there with me. Yes. Like that's what, yes. Okay. Now, why am I saying all this? Like, who cares? I mean, yeah, who cares? Well, what I care is that then we have this concept that you hear about all the time in the world called entropy. What I was trying to say yesterday on the board is so entropy is denoted with the letter capital S. Okay. First and foremost, what a change in entropy is defined. Oh, I could even say here. I forget if I've said this in this class, but if I ever use triple equal signs, if I use a triple equal sign, that means equal by definition. Like that is, I'm defining. So what is entropy in first and foremost? Like what does it actually mean to a chemist or, to a thermodynamical physicist? What does entropy mean? What it really means, well, what a change in entropy means is a change in heat divided by temperature. What entropy really means is how much total energy you have in a system per the average amount of energy in that system. That's really what it means. So, so it would be like, I mean, it's a little bit like I go to another professor. Here's an analogy, just really quick, and I think there's something in the chat. I'll catch it in a second. But I go to another professor and I'm like, dude, my class rocks. I have like the best MHC 225 class, like in the school. Like the average on their last paper assignment was a 10 out of 10. Like, okay, like my average is a 10. So how cool is that? I win. And then the other professor's like, yeah, but my class average is also a 10. And I'm like, oh, then I guess we're tied. Okay, but I mean, this is stupid, obviously, but then I'm like, oh, I guess we're tied, but we both have the same average in our class. But then the professor says, yeah, but can I point out, like, you have an average of 10 in your class, and you only have three people in your class. In my class, I have 30 people, and they all got a 10. So we have the same average, but there is some kind of meaningful distinction between our two classes. Like, really, you only, or if you want to go to the extreme, you only have one person in your class at this point. Everybody else dropped out. And so what? That person got a 10. But I have 30 people in my class. They all got 10s. And that's, even though we have the same average, I'm going to say, this other professor says, I'm going to say, what's happening in my class is noteworthy because a lot more different things could have happened. Like there was a lot they could have had, like they could have all had ones, they could have all had twos. There could have been a big spread of grades in the class. There was all these possibilities with 30 people, and yet we still all ended up with an average of 10. You have an average of 10 with only one person. So really, it wasn't as hard. It wasn't probabilistically, statistically as hard to achieve as the fact that, right? So they start putting some emphasis on this rate that basically they're like, we could talk about our averages, but they're the same. I'm talking, I have 30 people doing that average. So they start making a point of that number 30. That's what it's like to talk about entropy. It's saying not just how much motion do you have in this gas, not just the total amount of motion and not just the average motion, but really the ratio of the total motion to the average motion. That's what entropy is. The ratio. And, oh, there's someone here. Yeah. Okay. And I know there's someone in the chat. I'll get them in a second. But it's the ratio of of total per the average, which really means, if you're following my analogy or following the logic, it really means that when you're looking at entropy, you're looking at the number of different ways that the system of microscopic particles could have been arranged. That's what you're looking at when you look at entropy. To say that entropy goes up is to say that the number of different ways that something could be arranged, that the system could be arranged, has gone up. I'm going to pause for a second because there was something in the chat, I think. Oh, maybe there wasn't. Okay, there wasn't. Sorry. Um, Technically, everything I'm saying now is like a repeat from what I said 2 days ago, but I said it at the end. I think I said it kind of quick, and I'm trying to break it down now. Of course, even if I'm talking fast, it's to make sure that I get to it all. Like, but this is all we're talking about this period, so you definitely can and should ask questions. What? So I'm saying the first equation here, if you copy down these symbols, what the symbols mean, the first equation, and obviously I'm going to upload this PDF if I'm whatever. This first equation here is saying, strictly speaking, entropy is like a chemical concept. It's about heat and temperature. It's strict, but but it's a ratio of heat to temperature. And by the way, if you don't like those triangles, if the triangles make your brain fuzz out, then ignore them. The triangles are there for a reason. The triangles are saying some of these things we have to talk about, we really can only talk about when they change. It's kind of goes back to Clyde's question, honestly. Some of these things, like heat, is really best to be discussed when it's flowing in and out, in or out of a system, or when the system is rising or falling in heat. And same thing, entropy. Like we put the delta triangle before because we actually want to force ourselves always to only really be focusing on heat and entropy when it's going up or going down. Whereas temperature is that macroscopic description of a state of a system at any given moment. But so if you follow what I just said, that is great. But if it's like too much, then just the fuzz out the triangles and don't get bogged down in it. The main point of the first equation is that entropy means heat per temperature. And to see the difference between the two, or to see what that means, you want to remember that heat is total amount of motion and temperature is average amount of motion. But then that leads to that's that's like, I'll even say this. Oh, and I'm gonna skip to a second. During the 19th century, when this kind of branch of physics or chemistry called thermodynamic, when the study of heat started becoming a formal study, when people, yeah, when the science of heat flow, particularly of fluids, of gases and liquids, when it started being established as a formal science branch of science, there were laws of thermodynamics, the first law, second law, third law of thermodynamics, just like there's the first law, second law um, of motion in physics. And the second law of thermodynamics that you hear about all the time, again, I'm trying to explain, I'm trying to give you a slightly more insider view on aspects of science that I think make it to the real world all the time for what it's worth. Like this is not arbitrary. I feel like these things come up all the time in the New York Times or, Fox News, whatever, and it's worth having a little bit of insider perspective on them. So there's this thing called the second law of thermodynamics. It comes up all the time. And in short, in equation terms, the second law of thermodynamics says that all other things being equal, any given system that is not being acted on by the outside world, any isolated closed system will tend to increase its entropy. That's what that third thing is saying. Delta S um, Yeah, delta S is greater than zero, means delta S tends to be a positive number for any given system you look at. That means the change in entropy tends to be positive for any isolated closed system you look at, means that if you leave systems alone, if you leave a gas alone, like a gas in a container, and you walk away, the entropy, the natural state of that gas will be to increase its entropy over time. Like that's a law of thermodynamics. Oh, good question. Good question. Um, if it could, it would. If it can, it will. Now I'm saying all other things being equal, like if the container is strong enough, then the container is meant to hold the gas, so the glass will come as close as it possibly can to exploding. Right, right. I mean, that's a really good. Okay, so by the way, thank you, Ryan, and thank you, Annie. Obviously, at least two people are. Wait, okay. Did I? Did okay. Wait, so let me. All right, so let me take that seriously. What I'm saying is, if you put a gas into a container, I mean, if the container is weak enough, the gas totally will explode through the container. If the container is strong enough to hold the gas, okay, then that's an external force on the gas. But the gas will do everything short of exploding, like to the extent that it can explode, it will. And what that's, oh my God. Okay. Oh, wait. Oh, yeah. Oh, yeah. Well, let's be clear for a second. Like, yeah, I mean, gas doesn't always intrinsically have to mean dangerous. I mean, my example, when I say a gas in a container, it could be as simple as you have a pot at home, you put water, let's say, to a third of the height of the pot. Like you don't fill a pot all the way. You put, some amount of water in the pot. You close the pot and then you turn on the heat, on the stove top. And so you start boiling that water in the pot. I, like the water starts boiling and starts making all these bubbles, and eventually, steam starts coming out. But vapor, like eventually, I think you all know this. If the temperature of the water gets high enough, now a lot of that water will turn into a gas state, i.e., water vapor. Just like if you put ice in the pot and you turn up the heat for long enough, the solid water, will eventually turn into liquid water. Well, liquid water will eventually turn into water vapor, and the water vapor will be trapped. If you put a lid on the pot, the water vapor is now going to be trapped in the pot. if the lid is not strong enough, you know from experience, or you don't put it on securely enough, oh, that vapor can certainly be strong enough to knock the pot off and boil over. I mean, some of you have seen this, perhaps, right? If the pot is secure enough, or the top is secure enough, maybe it won't boil over. But in fact, even as I'm saying this, mostly, as you know, most pot tops these days, or many of them, have like some little valve or like little hole or something, so a little bit of vapor can escape. Because it's true, if you let this thing go long enough or you forget about it, like either the top will fall off and the thing will boil over, or it will break. Something can break for sure. I mean, I remember I taught third grade once, and I accidentally was heating water in a Bunsen burner in front of third graders, and the whole thing shattered right in front of them because I mean, it was a long time ago. And they never let me teach third graders again. So they forced me into college where it was safe. No, but yeah, you're absolutely right, is what I'm trying to say. For sure, it can explode, and even when it doesn't explode, like dangerously, something is happening to that gas that is called an increase in entropy. What, like that gas is, and even when you turn the heat off, it's going to keep increasing its entropy on naturally. And what does that mean? Like even people in the 19th century knew to say that systems naturally increase entropy in really simple terms. Oh, I'm totally going to look at the chat in a second. I see there's something in the chat. But what this last equation is saying in really simple terms is systems, and by systems, it's easiest to picture gases. I'm not saying it's only true of gases, but it's easiest to picture. Systems naturally spread out. That is what we're saying by this third law. I mean, this second law, the third equation, the second law, which people knew in the 19th century. I'm totally going to look in the chat in a second, but let me just try to tie this together. What I'm trying to say right now is what people knew empirically, like just from observation, the same thing that somehow an unwatched boiling pot will like boil over and like explode in one way or another. What people knew is that, or and even just on a simple term, you put your cup of coffee down on the table and the steam or the vapor, which are two different things actually, but the steam and the vapor from the coffee, the heat from the coffee rises up and spreads out through the room naturally. No one ever expects to see the heat from a room gather itself up and dive into a cup of coffee. That's not what happens, right? Naturally speaking, systems spread. And specifically, naturally speaking, heat spreads. That's the claim of this third equation. That's the claim of the second law of thermodynamics. What I'm here to say after I look at the chat, well, what I'm here to say right now and then look at the chat is that that's something people notice when they look at chemistry and heat flow and thermodynamics and gases and liquids. They have been noticing for centuries that systems tend to spread out when left alone. Which is like a thing to notice. Like I'm not saying it had, well, that's the way it is. Things tend to spread out. They don't tend to suck themselves in. But the interesting part of it, that's a macroscopic observation. What I'm trying to tell you, and I will take a breath in a minute and look in the chat, but what I'm trying to tell you with the second equation, which is more of these three, the second is a more modern innovation. It's a more modern realization. Maybe I should have written them in a different order, but I'm saying people understood that there was like heat and temperature. People understood that heat like spreads out. But then eventually a man named Boltzmann, this second equation is called Boltzmann's equation. He was at the turn of the century, of the 20th century. Boltzmann realized for the first time that, will mathematically pin down for the first time, that what's happening on a macroscopic level is really analytically tethered to what's happening on a microscopic level. He's the one, Boltzmann, that turned the study of heat flow into a study of what we today call statistical mechanics. Again, I know there's things in the chat. Just bear with me for a second. Because what I've been trying to say for a couple of days is the macroscopic observation, maybe write this down, the macroscopic observations of thermodynamics, the macroscopically observable phenomena of heat flow are today understood to be manifestations of microscopic realities of statistics and probability. I mean, I'll say it again. Macroscopic heat flow is a result of microscopic probabilities. And that equation in the middle is trying to say that in mathematical terms. The big omega means literally that big omega means number of different possible micro arrangements or micro states for any one given macro state. I'm going to elaborate on that again in a minute, even though I sort of tried too quickly on Tuesday. What omega stands for is the number of different ways you can arrange a system. K is a constant number called Boltzmann's constant. It's a number that makes all the units work out, that never changes throughout the universe. He discovered it. It's a point of pride. And ln means natural log of. It's a mathematical thing, which I'm happy to discuss with anybody if they want to in my office hours or blah 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 blah. But it's a mathematical function, logarithm, like exponent or something like that, which just means which you don't have to get bogged down in the moment. The point is that S, the measurement of entropy, is really a result of arrangement possibilities. That the more the number of different ways to arrange, the number of different microscopic ways to arrange a given macro state is what ultimately we mean by entropy. We thought entropy was just heat divided by temperature. It turns out that entropy is number of different ways that a system can be arranged. That leads to a very, very interesting conclusion about heat flow, I think. But I'll pause because I know there's things in the chat. Hold on a second. Oh, there's a lot. Okay, well, hold on. There's a lot. One second. Okay, some of it's funny. Yeah, I do appreciate that. All right, wait. Oh, it does make sense. Okay, is that how the? Oh, this whole study is, yes. I mean, the discovery of the steam engine is part of this 19th century study of thermodynamics. Yes, the steam engine predates Boltzmann. Like, they were able to understand enough about heat flow and entropy on a macroscopic functional level to develop like the Carnot engine and the heat engine. Yes. But the interesting thing, I guess I'm saying, is there was a deep understanding of heat and temperature enough that, yes, they were able to do things with heat, like make a steam engine, right? But then a little bit later on, not a lot, but a little bit later on, this guy Boltzmann said, all the stuff that we're playing with in the world, actually down below is just chance and probability. I mean, that's like a big. I hope you see. Again, am I saying you have to believe me? No, I'm not pretending that I've proven that at all. I'm trying to explain it and make sense of it. But I almost would be delighted if half the class believed me and half the class didn't believe me, because that would show that you see that I'm actually saying something that is not self-evident. I am saying that he's saying heat flow and gas, what we see up here, down here is like a bunch of deck of cards or a bunch of dice being flipped or a bunch of coins, which is a surprise. Wait, but I'm staying in the chat. So yes, that is how they discovered the steam engine. Who made laughing gas? Don't know. Fair enough. Okay, that's funny. That is funny. Okay, but then there's a direct. Okay, wait. Oh, yeah. Wait. There's a direct chat thing, which is fascinating. So I won't say the person's name, but yeah. Okay. Huh. Wait, okay, I'm looking to. Okay, wait. So something in the direct chat. Yes, yeah. Well, okay, I'm going to sort of read it out loud, but without a name. When I was working on the Arrow of Time assignment, it reminded me so much of the concept of increasing entropy. Right. That is what I'm trying to say. Yes. the arrow of time is yes. I want to clarify that it is because of the concept of increasing entropy that we always experience time moving forward from order to disorder, because it's extremely unlikely that all the dice would ever roll back into the same number again by chance. So, yeah, sorry, I should have read that more. The person is saying in direct chat is, do they have it right? They're asking, are they kind of like understanding it correctly? That 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 the point of the arrow of time assignment is that what we that the idea that things tend to move toward disorder, that idea of entropy, um, that is how we experience time, and that is actually the result of probabilities. Yes, I'm saying to the person in direct chat, yes, you are understanding. That is what I'm saying. And what I'm saying to everybody now is that's a big, like, it's really two things well, it's many things at once that I'm saying, but it's really two big things I'm saying at once. Number one, the idea that we experience time as going forward at all, that we experience any, remember again, I was trying to say Tuesday, we don't experience space as having a particular direction, but we do experience time. We experience time as having a particular direction. And the first thing I'm kind of asserting, or like, why we're now talking about heat, like, how did this class get us involved in talking about heat and chemistry and temperature? The reason is I'm submitting to you that the only times you ever really experience a forward notion to time, a forward motion to time, is really in when things spread out or get hotter, which turns out to be kind of the same thing. Like there's a lot of systems in life that act the same way forwards and backwards, like pendulums, like a lot of even things that we use to measure time, pendulums going back and forth, or balls dribbling up and down. Those systems are symmetric in time. They don't give you, they give you an idea of time. Like metronomes keep time for musicians. They totally give you a notion of time, but they don't give you a notion that time is moving in any particular direction. Right? Think about that. Like rhythm is a huge piece of time, but it's not apparently the only piece, because rhythms don't have to go forward any more than they go backward. They just go. They're cyclical. But many processes in life do give you it. Like, again, I'll just repeat, like if I showed you a movie of steam coming out of a coffee cup, but I played the movie for you backwards so the steam was going into the coffee cup, or I showed you a movie of a car backing up down the street while exhaust got sucked into its pipe, right? You would know that I showed you the movie backwards. You wouldn't be right. With some processes are not that, but if I showed you that, you'd be like, wait, that's not right. You just played the movie backwards. You know it doesn't work. And people, and ultimately, life moves from birth to death. It doesn't go the other way around. What's really going on there? I'm ultimately arguing there are systems that are breaking down by spreading out in the body. And spreading out is now back to the direct chat person. Spreading out means increasing entropy. What people will say in the New York Times or in the world or whatever, they'll say entropy is disorder. Okay, where I'm now really trying to go with this is I think disorder is a confusing word. I think disorder is, I'm not saying it's wrong, and I'm not saying it's wrong if you use it in direct chat or even in the assignment, but use it carefully. When we say disorder, what we really mean now, ironically, when we say disorder, what we really mean is equilibrium, which actually sounds like order, doesn't it? This is where I'm going with this. Oh, sorry. And there was more in the chat. I'll look in 1 second. I just want to say systems spread out. You can say that they get more disorderly, but I don't really know exactly. When I really think about it, I'm not sure what is order and what's not order. This is what I know. I know. Wait, I'm just looking at the chat. Sorry. Wait, actually, I'll pause for a second just to see. Wait, the chat. Well, okay, I guess this will tie together. I'm gonna call on Annie in a second and get back. I'm looking at the time. Wait. Well, here, wait. I know Annie's gonna. Well, okay, I'm looking at what Annie wrote in the chat. I might as well not even try to respond to it. Just yeah, Annie, go. Assuming you're going to develop what you just wrote in the chat.
No, I was gonna say like you mentioned how like disorder is a kind of like confusing term that it really means equilibrium. Is it also the same concept as like things getting more like homogeneous?
Right, right. Perfect, perfect. Let me write. Perfect. Yes. So, and that's why I don't love the words order and just. Yes. Let me write that. Hold on. Yes, yes, yes. And yes, great word that you. Nice to bring it back to the other. Okay. The, sorry. Okay. Yes, yes. Like, with all due respect, since I think we are all in the same, like, what I love is what Annie just said. And I love it more, to be honest, than what you put in the chat. Like, I mean, which is funny what's in the chat. But the reason I'm bumping over the thing in the chat is like words like worst and good and or bad and good or even order and disorder. Like those are value judgments which are interesting, but we sort of want to come to later in our own heads. What I really agree with is that if you, this whole idea to bring it back to Ryan's and other people's thing, the idea that you would expect that somehow like a gas could explode a container or that the top of the pot of boiling water would fall off eventually. What that's about is that the systems let, if all of the things are equal, the tons and tons and tons of particles that a gas is made of, they, when we say they want to spread out or they tend to spread out, what they're doing is getting equally distributed throughout a space. What we're saying is if you let a system alone long enough, eventually you'll have one particle over here and then a cubic centimeter away, or yeah, a cubic centimeter away, you have another particle. And then a cubic centimeter away, you have another particle. And then a cubic centimeter away, you have another particle. Eventually, things will be spread out uniformly, equally. Eventually, all the little pieces will occupy the space in as even a distribution as is possible. That's the claim. Um, as opposed to, so coffee, I mean, yeah, so like the vapor or the steam from a coffee cup will eventually spread out throughout the whole room and will spread out evenly. Like there won't be clumps. This is what I mean by uniform distribution, or what Annie means by homogeneity or homogeneous, or what we could call equilibrium. Systems tend toward equilibrium. But let's be really, but I mean I learned that okay. I well, first of all, I'm going to pause for a second. Whether you do you just raise your electronic hand if you even can follow that statement that systems, if they're left alone, will tend toward a state of uniform distribution. Like, can you picture what I'm saying? Even if you don't agree with it, can you picture what I'm saying? When I, that awesome. Thank you, Maya. Oh, that was thank you, Maya. That and Emily, thank you. Awesome. Okay. Okay, then the reason I think that that's good enough for me, thank you, and you should definitely submit for points. Okay, so why that's now again, now you can see why I'm not sure that that's disorderly, right? I mean, if you have like one dot over here and one dot over here and one dot, and by the way, this is what we think is happening with the universe, right? We think eventually, if the universe is left to its own devices, event, some people even call this heat death. Like some people will say that the fate of the universe is heat death, like one particle being over here, one particle being over there, just everything spread out as evenly and uniformly as possible. Now, again, that may be really bad. Like I might not want to experience that, but I'm not sure. I don't think that's disorderly. Like it's about as orderly as it gets in some ways, right? What it is, though, is uniform distribution. And why, and people have noticed that systems tend toward that and that heat spreads like that if left to its own devices. It seems to be a law of the universe that things just do that. And that to indicate and the difference between future and present and past is that future looks more uniformly distributed and past looks less. Oh, great. I'm going to get you in 1 second, Maya. Awesome. I'm just going to try to land this little plane, which is what I'm trying to say. If you're putting these pieces together, there's a lot of pieces I've been sort of trying to put on the table for days, but I'm trying to say that's something we observe that seems to be true, and it just seems to be true. But there seems to be a reason for it. If you look deeper, I'm just going to say this once and then get Maya. I mean, I'm going to try to say it slowly again, like I said at the end of Tuesday. If you think about it, there's many, many more ways to have all the particles of a system distributed uniformly throughout a space than to have all the particles occupying a tight, unspread out, undistributed space. Like having a deck of cards, and I'm not going to forget about Maya, I promise, but having a deck of cards with the kings spread out throughout the deck there's more ways to do that than to have all the kings right at the front, to go king, 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 king. There's only one way well, maybe there's four. I mean, to have king, 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 maybe there's right there. I mean, there's only 4 spots and there's 4 kings. That's it. But to have a king over here and a king over here and a king over here and a king over here, well, it could be the first king over here, could be the second king over here, could be the third king over here, et cetera, et cetera. To have like if so, to have everything spread out equally doesn't mean it has to be particle number one in space number one. It could be particle number one in space number one, or particle number two in space number one, or particle number three, et cetera, et cetera. Same thing with space number two. To have everything spread out, there's many, many, many more ways microscopically to bring about that macroscopic arrangement than there is to have all of the particles in one spot of the room. What I'm trying to claim is the idea that things tend to go toward uniform distribution is a way of saying that there's more ways to arrange uniform distribution than there are non-uniform distribution, so that if you wait long enough time, that would eventually tend to happen. I'm saying it's not that things are trying to do that. It's not even that things have to do that. It's that if you waited long enough, it makes sense that that would eventually happen just by chance. So that what I'm saying, and then I'm going to get Maya, is that what seems to be the direction in which life is trying to head is just, in fact, the direction in which life ends up landing by chance. I mean, that is a big statement. But that's what we're saying. We're saying the arrow of time is really the arrow of increased likelihood. That's what this means. Okay, Maya. Sorry.
Um, so my question is like, what does that mean for a system to be left alone? Because doesn't that never actually happen in the real world? So how would that be applicable? Like if nothing exists in a vacuum, then why is it relevant that a system does this when it's left alone if it'll never be left alone?
That's a great, 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 great question. Okay, I do think I can answer it, but it's a great yes. Okay. Um, I don't know of any system that can perfectly be left alone. And just like I don't know of any like object, like mechanical object in physics that can literally have no friction on it. Like, I mean, I don't know any like normal object. So that's true. But here's what, when we say these things, here's what we're really saying. We're really saying a relationship. We're really saying the less intrusion there is on a system, the more true this claim seems to be, right? Which is a different kind of state. Like, well, yeah. So I'll say that again. First of all, what we're really saying is the less you mess with a system, the more this tends to happen. Or put another way, the more you mess with the system, the more you're interfering with this tendency. So it is very, very possible to compare systems, to look at systems with less intrusions on them than others, and see that this phenomenon is more true, even if it's not perfectly true. And in fact, it's possible to put all these systems like on a graph and start seeing, and this is really what really does happen in science. And that's why I'm glad you're asking. Like a lot of things in science come across like idealizations. Like in the ideal world, in a perfect vacuum, this is what we believe would happen. And then the rest of us totally look and we're like, well, that's great, scientist, but like I live in the real world. You're talking about some ideal world that doesn't exist. What's the point? What they're really trying to say is the closer we get to ideal conditions, the more this is true. And wait, so far, hopefully, well, tell me if that, so far, that's what I'm saying. I'm saying systems that are less intruded upon demonstrate this more. And it certainly is possible to make systems that are very, very, very much not intruded upon. There are not perfect vacuums, but darn close, but in the laboratories. But then I'm going to go a step further. Well, wait. So, okay. So number one, the purpose of all of these claims is we're isolating variables. Like when yeah, we're isolating variables. We're saying we can get things down to the point where, say, the friction or the interference is so small that, yeah, we see a small result of that. But since it's really small and nothing else is going on, we now know that that result that's happening, that annoyance, is connected to the friction. Like we can isolate the friction or whatever the intrusion is and actually study it unto itself, which we do. So it's not like imagination or guesswork, even though it sounds like that sometimes. But the other thing I want to say, because it's a really great question, is that one of the differences between science and math is kind of perfect, right? I mean, you might hate it. I mean, I don't know how Maya feels about it, but like some people might hate math, but part of why they hate it is because it seems so absolute and rigid, right? I mean, like the fact is a square has four sides, right? It is a mathematical reality that a square has four sides. And you all know that uh, if I came to you and said, I was in Philadelphia the other day and I went to a museum and I saw a three-sided square in the museum, you would know not to trust me. You know I was full of crap in saying that. And it doesn't matter. And if I said to you, well, what really? Like, and you would challenge me. And if I said, well, have you ever been to Philadelphia? Have you ever been to that museum? How do you know? You'd be like, dude, it just doesn't even work that way. Like, that's not how that works. Like, square means four sides. Like, you're just not getting it if you think you've seen a three-sided square, right? And all of math is actually, it's all a bunch of definitions like that are just like really elaborate and precise and symbolically intimidating sometimes. But all of math itself is that way. It's analytical. It's like 2 + 2 = 4 because that's what we mean by 4 and 2 and this and that. And so that's either what you love about it or you hate about it sometimes, that math is perfection that way. If you think it's true at all, it's perfectly true. If you don't, you don't. Great. But now science is not that way. This is what Maya's getting at here. I mean, science is not math. Science uses math as its language, but science is not math. Science is us interfacing with the real world of matter, energy, space, and time. Where am I going with this? The way we interface with the real world in science is measurements. Measurement, reproducible, yeah, reproduced isolated conditions or controlled conditions measurements is where we get our data and our basis of truth in science. Why I'm saying that is if in the and so we only trust science as much as we trust the measurements. And then we do math to the measurements. But if in the end of the day, the measurements are the arbiter of truth in science, then on the one hand, that's what makes Maya's question totally legitimate, totally real. She's basically saying, hang on, have you ever have you ever made measurements in a perfect vacuum? Or has like any scientist in a lab ever made measurements in a perfect vacuum? The answer is no. She's right. And no scientist has ever gone to deep, deep, perfect outer space that's literally infinitely far from like every other particle in the world. No one has. And it's not a BS point. Like it's a very fair point. But here's the flip side of the point, if I haven't lost everybody already. No scientist has ever made a measurement in a perfect vacuum. However, at the same time, if a scientist really trusts only measurements as opposed to his or her own head, if what we're writing down is the measurements, then measurements are only as good as the precision of the measuring tool. And no measuring tool is infinitely precise. By definition, no measuring tool is perfect. So you really want to think about that for a minute. Like when we write down measurements in science, we are always right away writing down a range of possible values. We're always writing down an uncertainty right away because like if you say something is 1.5 inches, you mean it's closest to the 1.5 inch mark on the ruler. It's between 1.5 inches, like 1.25 inches and 1.75 inches, or whatever level the lines go down to. That's all you can say. You literally, as a scientist, do not say it's exactly 1.5 inches. You say it's between 1.25 inches and 1.75 inches, or like whatever. So that means that as long as your vacuum is as good as your measuring tool, as long as the flaw in your vacuum or in your conditions is smaller than the level of precision of your measuring tool, then you are making testable, precise claims that advance the science. I mean, that was a long answer, but I really want, I'm good. And it's not an argument against Maya. And I'm telling you, it took me 20 years of doing this before that hit me as like an astounding distinction between science and math. Like in science, we don't deal with perfection, but what we deal with is measurement. And we know that measurement is not perfect. So what it always is a competition between the imperfection of the measurement and the imperfection of the system. As long as the measurement is better than the system, then we've learned something and we write it down until the next generation when they get a better measurement and, et cetera. But so if you know what an asymptote is, any of you, if you know what an asymptote on a graph is, that's what science is about, is approaching the asymptote. We're never getting there, but we are always getting closer. That's the idea. I mean, that's the hope. That's the belief. I don't. So I don't know if I hope. I mean, I think that was a great question. Oh, follow up from Maya. Okay, yeah.
I do have a little bit of follow-up, which is just like when you say that the vacuum has to have less flaws in it than your measuring system, um, like how do you measure that? I don't completely understand that.
Yeah, I mean that's fair. It's like a big, but thank you for pressing on because that's exactly the right. I mean, thank you for like engaging with that. Right. So it's a little bit hard to, but basically, let me put it this way. Say a flaw in a vacuum means say that a vacuum is not perfect means there's actually a particle in it. Like a perfect vacuum would be no particles at all, right? And you're completely right. Like we can't construct literally no particles in the lab. Like they try and they get shockingly close. Like they actually, well, okay, different. They can produce, it's actually true. Just, okay, I said deep, deep outer space is like 3 degrees Kelvin. That apparently is true. In the lab, if you look this up on the internet or whatever, there are laboratories where they could create temperature conditions that are within 0.00001 of a Kelvin of a degree. Like they can get really cold, i.e., really close to a vacuum in a lab, like much closer than I would have ever believed, which is already interesting. But it's still your point. Like it's still definitely not zero. It's okay. So what does that mean? It means that even though they try to suck all the particles out of like some chamber, there's still some particles that they can't Get rid of and that they just they know to be there. But what I'm saying is then imagine that every measurement they make that's relevant, that they're trying to figure things out, if every measurement they make, if the number of particles is smaller than any count that they could come up with on the measurement device, then that's what it means to say they're negligible, or they're in, if you've ever taken calculus, like they're in the limit as the number of particles approaches zero. Like what I'm saying is a lot of experiments are like, we know enough to know that there's a flaw here. We know enough to know that there are particles, even though we wish there were none. But the number of particles is so small that even though we know it's not zero, it's bigger than zero, it's smaller than any number that we have any capacity to quantify on any measuring tool. It's that small, right? Like, and they can do that. They can literally get it down to, they know it's not perfect, but the level of imperfection is not quantifiable. So then what we say is, from a measurement perspective, that's falling between the cracks of the measuring tool. Like literally, like it's like we don't, like there's particles there somewhere, but we can't even identify one of them. We can't count them. We can't like track it. Yes, we know it's there, but we can't. So then we say that's below the threshold of measurement. And it doesn't mean that we don't ignore it, right? Like you and I are both admitting that that's, and in the articles, they'll admit here's our uncertainty or whatever. But but to say something is below the threshold of measurement then means, okay, that's beyond, like then we can't talk about it. Only philosophers or theologians or anybody else, they can talk about it. But we as scientists, like that's now above our pay grade. All we can talk about is what we picked up on our tools. So now we're going to start talking and like making whatever conclusions we are about what's on the level of our tools. I mean, I don't know if that, so I'm basically saying, imagine, and that literally, if you've ever done calculus or been intimidated by calculus, whenever they say limit as blah, blah approaches zero, what I really take that to mean as a scientist is it means bigger enough than zero that we recognize it's there, but small enough that we can't quantify it. And that's a zone that's interesting to think about, but not a zone that science can like infer things. You can't make conclusions about that zone. So we make conclusions about all the other zones. And they work. I mean, okay, it's like if I sound a little defensive, I am, because of course I'm like trying to protect my baby, which is science, but I love that concern. And it's been my concern. If I sound like I have an answer to it at all, or it's because I've had that concern for years. It's not an irrelevant concern by any means. But it's kind of why I like math in one part of my brain, and I like science in another, and I like theology in another, and they're all ultimately related, but there are different ways of thinking. And in the scientific way of thinking, what I'm really trying to say, to make a much more concrete example, and then I'll shut this part down, like just the idea that Newton's law, Galileo's principle, that we think like a hockey puck, if left to its own devices, if you put a hockey puck on really frictionless ice, like perfectly frictionless ice, we think the hockey puck would keep going forever in a straight line at the same speed, right? And that's like Newton's first law, if you like. Maya's question really is kind of like, well, what's the point of that law if you're never going to get perfect ice? Like, and you're never going to see a hockey puck perfectly go on straight forever and not slow down at all. My response is, right, you're never going to get perfect ice, but here's the deal. You can get ice that is so smooth that the level at which the hockey puck does slow down, you can't pick up on your measuring devices. That's what I'm really saying. Like, the hockey puck will maintain, and this can be done lab, and this totally is done on the moon and stuff when they went to the moon. Like when you throw things in outer space, even in outer space, it's not a perfect vacuum. They wouldn't literally go on forever. They wouldn't literally never lose speed, but they won't lose speed at any level that any human being could pick up on any measuring device. You see so as long as it remains constant to the level of measurement, then it becomes a scientific claim that it's constant. Our Supreme Court is the measuring tools. That's not the only Supreme Court in the world, but that's the Supreme Court that defines scientific truth. I don't know if that, I mean, again, I'm like leaning in because I think it's a great question. I don't know if it really. Oh, great. Thank you, Maya, for the chat. Okay, great. And both for the question and for the. Okay, now it's 10:35, so I'm gonna. I love this though, and for what it's worth, I still want to say more, but I've certainly said enough now that I think you can do the homework. Like I don't think like you need. Okay, but I am going to say a little bit more because I what I'm trying to say, I'm going to say it again. Things that tend to happen. The argument is they tend to happen because they're more likely, not because they have to happen that way. That's the argument. That the arrow of time is the arrow of high probability. I mean, that if you're really listening to me, and I mean, clearly Maya is, clearly Annie is, clearly Ryan, I mean, clearly a lot of you are. If you're really listening to me, if in any way through your brain you're saying, wait, so is he arguing that like it could possibly be possible to like go back in time or do so, like is he saying it's like not definite that time has to go forward? Certainly if you're thinking that, you are hearing me. I can't tell you. I don't know, but yes, I'm saying what according to what science knows so far, we can't prove to you that time has to go forward in this way. I mean, some people believe it does and some people believe it doesn't. But it's up for thought once you understand the arrow of time to be. So it's like this. It's like this. Sorry. To bring it back to Darwin, which is what started this in the first place, like one of the things that's sort of revolutionary about Darwin that troubles some people sometime, and maybe it should, or maybe it shouldn't, is wait, do I want to say this? Survival of the fittest or natural selection is much like this in the sense that we're saying it's a matter of probabilities. If we believe Darwin, or Darwin is saying that the fact that things tend to evolve towards more and more fit states, according to the Darwin way of thinking, it's not that species are trying to do that. It's not that anything is trying to do that. According to the Darwinian way of thinking, it's not that there's a goal that species should be more fit. It's that really lots of random things happen. Lots of changes occur all over the place all the time. And the changes that promote survival by chance, the changes that are more beneficial to competition in a low resource environment, the changes that happen by chance to be more beneficial, well, those then survive because they're better for survival. So then they get passed on to the next, so that species develop traits that are more and more fit for survival, not because of a program or a plan. And again, I'm not saying what's right or wrong. And I hope it's clear already. I have a lot of beliefs myself that are not like, but I want you to know what the story of that is, that there's just a bunch of chance that's going on, but that things tend toward higher probability states rather than lower, simply because there's more ways to arrange a higher probability state than a low probability state. Or so what equilibrium is the state that things tend to. So bottom line, if you shuffled a deck of cards for a long enough time, you would not expect to see ace, two, three, like, or ace, 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 two, 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 three, three, three. Over enough shuffles, you just wouldn't expect to see that, because there's only one way for that to be true. But you would expect to see something you might consider disorder, but really would be a uniform distribution. If you shuffled a deck of cards long enough, you would expect to see no pattern at all, which really means to say things spread out equally throughout, because there's that many more ways for that to be possible than for things to be in specific locations. So over time, things fall into macro states that have that many more micro arrangements possible. That's what we consider the flow of time to be. We in this branch of science, we consider the arrow of time to be a flow from very few ways to arrange a system to very, very many ways to arrange a system. And and that's what it is. Okay, so okay, we'll move on to other topics next class, I promise. But thank you for hanging in there with me, and have a great night. Yeah, time's up. Right. That's why I said, yeah, bye-bye. Right. That's why I said,
Bye. Thank you.
Well, Professor, thank you.
bye. Thank you.